In this lecture, we'll define measures of information for continuous valued random variable. In particular, we'll define mutual information and differential entropy. In order to define these quantities, we need to generalize our definition of Kullback-Leibler divergence, which we have seen earlier for discrete distributions. We want to generalize the definition to general probability measures P and Q. Um, in fact, in fact, uh, it's not even in this course we will not be able to define what we mean by general probability measures. But you can imagine something which is more general than continuous or discrete random variables. You can imagine, let's say, mixed random variables or something even more general. Okay. So just to motivate the definition of Kullback-Leibler divergence for general random variable, note that for discrete random variables, for two PMFs probability mass functions P and Q, such that support of P is contained in support of Q, if I give you any set A and ask you to compute its probability QA, which is simply summation over X. Actually, support of P is contained in support of Q. So let's say I ask you to compute P of A, which is summation over X Px. I can multiply and divide by Qx. Note that here we are only looking at those Px where X is only those X where Px is not equal to 0. And since Px is not equal to 0, Qx must not also be 0 because by this condition. So I can multiply and divide by Qx. So we get this. So if I call this function here, this guy here, if I denote this by some function g of x, then this probability simply becomes summation over x gx qx. Therefore, if you want to convert the probability over p to probability over computation over q to probability of p, you have to multiply with this function gx. In fact, by the same calculation, the expected value of a random variable over p, okay, is equal to summation over x px denoted by something else. Expected value of, let's say, some function f of x over p is expected value over carefully, expected value over p of f of x is equal to summation over x px f of x. But then again we can multiply and divide by q, so you get gx fx qx, and this is nothing but the expected value over q of gx fx. Okay, so what's the point of this calculation? What this is saying is that we can convert expectation over p to expectation over q by multiplying with this function g. Okay. And this function g, this notion of g, which we just saw, which is just this ratio of PMFs. This concept of this ratio of PMFs can be actually extended to any general probability measures. It need not be for discrete random variables. And the only thing we want to generalize is this condition that the support of P is contained in support of Q. This was used here. If this condition doesn't hold, that this ratio may not be defined. It may become infinite. But under this condition, this ratio is well defined for those for those points where Px is positive. Even for those points where Qx is positive. And so turns out that this notion can be generalized to very general set of measures. And there is a result which tells you that, and this result is a result from measure theory or probability theory, and this is called the Radon-Nikodym theorem. So what does this theorem say? So it says that suppose P is absolutely continuous with respect to q. Okay, so this is p is, I'll define what this means. Absolutely continuous with respect to q. What does it mean? That is, if q of a equals to 0, then p of a must be 0. Okay, so this condition basically generalizes the condition support of p contained in support of q. Okay, so that was the condition we used in the discrete case. In general, this is the condition that whenever p of q of a is 0, then p of a must be 0. Suppose this condition holds. Okay, and for discrete case, this condition holds if and only if support of p is contained in support of q. So suppose this condition hold, then we can find a random variable, so just a function gx, such that for every f, the expected value under p of fx is equal to expected value under q of gx fx. Okay, so basically this g this g this thing always exists, and this gx can be viewed can be viewed can be seen as the density of p with respect to q. So to understand this, when you think of a regular probability density for continuous distributions for continuous random variables, you integrate with respect to the standard Lebesgue measure, but you multiply that integral with density, because this density allows you to convert the measure coming from from that standard integral to the probability measure. Just like the density of an object allows you to convert uh, volume into mass. And so this thing has the same heuristic significance. It allows you to convert integral over q to integral over p. That's why it's called density, and it has a special notation. This gx in a more formal language is also called the radon Nicodemus derivative of p with respect to q. Okay, so so this abstraction, what it allows you to do is, just like you can think of density of a continuous random variable with respect to the Lebesgue measure, now you can think of the density of one probability measure with respect to another one. Okay, and then it's called the radon Nicodemus derivative, and it's denoted by dp by dq. Okay, so this is a bit of a strange notation. There is no derivative here. If you want, this derivative can be within quotes. But why do we have this notation, and why do we call it the derivative? Well, because here is the reason why this notation is handy. When you are taking expected value with respect to p of some random variable x, one notation you can use for it is x dp. Okay, that's like integrating this function. Remember, random variables are function in formal probability. So this is a function, you're integrating it with respect to this measure, the probability measure dp. And now, as I said, we can convert it to an integration with respect to q by multiplying with this density. So it becomes x uh, dp by dq. Now, but you now integrate with respect to dq. That's the conversion, right? And the reason we use this notation is so that we can formally cancel them. This is just some never cancel a derivative like this, but this is just some formal thing, and it gives you this integral with respect to dp. That's why this notation is good to remember. In fact, these rules can be this formula justifies this notation. It behaves as if it's the ratio of dp by dq, but it's this function g, which is the density of p with respect to q. Okay, so that this function is called the Radon-Nikodym derivative. Okay, all right. So some examples. So when p and q are both discrete, distributions. So this p is absolutely continuous with respect to q if and only if the support of p is contained in support of q. This is an exercise, you can do it yourself. Okay, and if p is absolutely continuous with respect to q, its Radon-Nikodym derivative, which exists by Radon-Nikodym theorem, is exactly the ratio of their PMFs. So this dp by dq is a function of x, it's the ratio of PMF. Okay, maybe I should use the notation not x but something else, maybe y. Okay, all right. So okay, great. So this Radon-Nikodym derivative for a familiar example of discrete case is just the ratio of PMFs. In fact, when p and q are both continuous and have densities, let's say fp and fq with respect to the, so when I say density in standard language, that's always with respect to this big measure, the standard length measure. Then if p is absolutely continuous with respect to q, then dp by dq is equal to just the ratio of densities. Okay, so again in this case, just like this case, the Radon-Nikodym derivative is just the ratio of densities. And indeed, you can use the, if you multiply with this ratio, you can convert probability that is calculated with respect to p to probability calculation with respect to q. All right. So why did we define this Radon-Nikodym derivative? Because this can be used to define divergence between two distributions. So we are now in a position to define the Kullback-Leibler divergence between p and q. The divergence dpq is defined as the expected value with respect to q. Q is the larger measure. P has density with respect to q. The density of p with respect to q, the Radon-Nikodym derivative of p with respect to q, log dp by dq. And this is true when p is absolutely continuous with respect to q, and otherwise it's infinite. Okay, that's the definition of divergence. But remember, when we multiply with this density like this, this expected value over q, you multiply things with this density like this, log dp by dq is also equal to expected value with respect to p of log dp by dq. right? Because that's the, if you want to convert this integral with respect to p to an integral with respect to q, you have to multiply it with the density of p with respect to q, and which is this thing. So these two are also equal. Okay, so that's the general definition of these two are equal. So that's the general definition of Hedo-Nicodim derivative, and you can check based on these examples that I just gave that for discrete case this just becomes the standard summation px log px by qx, and for the continuous case it will become integral over fx log fpx by fqx, integral over fpx log fpx by fqx. Okay, all right. So now that we can define this, uh, we can also define mutual information as before. Okay. So mutual information between x and y, general random variable x and y, they can be continuous valued, is simply the divergence between pxy and pxpy. Okay. So it turns out that uh, all the results that we saw earlier for hypothesis testing, where we saw this operational significance um, of dpq, remain valid with this dpq. The only change is that the log likelihood ratios will be replaced with this log of this Redon-Nicodim derivative. This Redon-Nicodim derivative is essentially likelihood ratio. So remember what was the test that we developed that attains Stein's lemma? It put a threshold on log likelihood ratio. Now that test will be replaced with another test which will put a threshold on this log of dp by dq. That's the more general version. Okay. All right. And in fact, more importantly, our if you see our single shot proof of achievability for the channel coding theorem, that used the test for independence. Okay, and that result, the single shot result for achievability part of Shannon's channel coding theorem still holds with. So there we were asking to begin with, we asked some bound for ratio of densities pxy by pxpy. Now that will be replaced with this Redon-Nicodim derivative with pxy by pxpy. So earlier we saw this guy and we had a log of this replaced with the Redon-Nicodim derivative of this guy, replaced with log of Redon-Nicodim derivative. Okay, so the single shot result of achievability that we had earlier still holds. Again, I'm stating this without proof, but you can check. Nothing really changes in the proof. Okay, so we do have a single shot result, which we'll evaluate later. Okay, so mutual information is there, and we have this nice single shot result. We'll come back to that later when we are proving the achievability part of of the capacity theorem for Gaussian channel under power constraint. Okay, so we now sort of are convinced that divergence can be extended to general probability measures, and and therefore mutual information can also be defined because that's just divergence between pxy and pxpy. But how about entropy? Entropy by definition was a discrete random variable. Okay, so why was it a discrete random variable? Well, even the operational significance that we gave for entropy, it was the size of a large probability set. We saw that the size of a large probability set is roughly 2 to the power entropy. Okay, that was size of a large probability set and cardinality of a large probability set. And when we are thinking in continuous space, the cardinalities are always infinite, and so the entropy doesn't make sense in that space. However, what is the counterpart of cardinality in the continuous space? This counterpart is volume, and therefore you can ask about volume of large probability set. Okay, this gives us an idea of how to extend entropy to the general continuous space. But well, volume is actually a much more complicated object Then cardinality. Volume of a large probability set first requires you to tell me what is the dimension of that set, because you can only compute volume in an appropriate dimension. If you try to compute volume of a line in the 2D space, that volume is 0, but in the one dimensional space, that volume is the same as length. Similarly, volume of a square, a flat square in 3D space is 0, but in 2D space it's the volume of it's the area of the square. Therefore, volume is inherently tied up to the dimension of the object, and so to formally define this thing, we will need to define dimension of an object. And defining this dimension is a topological notion which is beyond the scope of this course. Uh, if you are interested in this part, you can look up in an excellent textbook on information theory for continuous systems by Ihara. But here, I will just say that the concept which replaces entropy in this volume of a large probability set is something called differential entropy. This differential entropy is the counterpart for entropy because it measures, in some sense, the volume of a large probability set. Okay. So remember that suppose P and Q have densities Fp and Fq. Then, so they are continuous random variable, the vanilla continuous random variable with densities with respect to the Lebesgue measure. Then the divergence between P and Q can be written as integral Fpx log Fpx by Fqx dx. But then we can again express it as we have been doing before, as integral Fpx log 1 by Fqx dx minus integral Fpx log 1 by Fpx dx. And this quantity here, earlier when we did this expansion, we had entropy on this side, but this quantity here is the differential entropy of P, and it's denoted by small h of P. So I know that we had used this small h for binary entropy, but it's the same notation we'll use here because you forget about binary entropy in this chapter. Okay, so this is a differential entropy. Okay, so right, so we defined it only for probabilities with this density, and it looks exactly like the formula summation over x px log 1 by px dx, but it's now summation integral fpx log 1 by fpx. Okay, so now what we will do is we have now obtained this differential entropy. We have obtained mutual information in terms of Kullback-Leibler divergence, and we will now note some basic properties of these quantities. So this is some basic properties. Of measures of information. So we had earlier spent a lot of time in defining the measures of information, giving a motivation for each of them, an operational motivation, and then we covered their properties. And in this lecture, we have actually just gone from defining them to reviewing this. Now we are reviewing their properties, and the reason is that the essential properties and the definitions are very similar. The technical difficulty is added by mathematics, which is anyway beyond the scope of this course. But what I have tried to convince you is that most of the definition just go through by some small changes. Okay, so in the similar vein, most of the properties will go through. So the first property that I want to look at is the data processing inequality that we had seen earlier, and it still holds. So if you look at the divergence between the output distribution of a channel W when the input distribution is P and QW. This is just less than equal to dpq. Of course, you have to argue that if P and Q have density, if P is absolutely continuous with respect to Q, then PW is also absolutely continuous with respect to QW and all that. All that is true, and then this inequality holds. Similarly, this is 1. Similarly, so if you have a Markov chain for U, X, Y, V forming a Markov chain, we have that the mutual information between U and V is bounded above by the mutual information between X and Y. Okay, the further away guys are smaller than closer guys. This is again the data processing inequality for mutual information that we saw earlier. So this is the first property that we have reviewed. All I'm saying is that data processing inequalities that we saw earlier extend to this more general measures of information which are valid for general random variables. Okay. The second property is about the connection between mutual information and differential entropy. Okay. So suppose we have a channel W from X to Y such that for every X, Wx has a density. Okay, the distribution Wx has a density. Now this is the situation. This is what happens in additive white Gaussian noise channel. This is what happens in additive Gaussian noise channel. Okay, so it has a density for every X, that channel. Suppose this is the situation. Then if you look at the mutual information between X and Y, that is equal to entropy of Y, entropy of P of Y minus expected entropy of this guy. Okay, this is essentially equal to H of Y. We can use the notation H of Y for this, minus I'm defining this conditional entropy. So this conditional differential entropy is slightly complicated object. It can be defined for this guy, and so you can define this, but you cannot define the conditional entropy of X given Y because X is a discrete random variable. It doesn't have a density. Okay, that's why this is a bit of a complicated, delicate issue. So in this direction, you will talk in terms of differential entropy. But if you write it in the other direction, okay, X does have a PMF given Y. So this is also equal to H of X, which is now a discrete random variable, minus H of X given Y. But these two things are very different from one is differential entropy and one is conditional entropy. And this is a bit of a delicate thing to switch between this form and this form. Okay. So these things were taken for granted for discrete random variables because we could just stay in the world of entropies. Both were continuous random variables, both were discrete random variable. But when you have this situation like a Gaussian channel, then input would be discrete and the output would be continuous, and you will have to talk about mutual information between a discrete and a continuous random variable. So you should keep in mind that either you can expand in terms of differential entropy minus differential entropy or entropy minus entropy. Note that Y does have a density here. The density of Y is given by the average density of Wx. Okay, that's why you can talk about differential entropy of I. Okay, so these two properties are sort of extension of the earlier properties that we saw. But the final property that I'll present is essentially a new property. It's only for this continuous case, and it's very important for us. This is the property that just like uniform distribution maximizes entropy, and we saw that also geometric distribution maximizes entropy among all random variables with given expected value. The claim now is that the Gaussian distribution maximizes differential entropy among all random variables, among all random variables, okay, with bounded second moment. Just like just like uh, we saw that geometric random variable maximizes entropy among all random variables by bounded first moment. For differential entropy, that job is done by uh, Gaussian distribution. All right, so let's show this. So let and then that random variable need not even be IID. So let uh, xn taking values in n length vectors satisfy expected value summation I equal to 1 to n xi square. So this is the variance with second moment of xi. So this guy, by the way, is just the, don't know if you know this notation. This is the Euclidean norm square, and suppose this is less than equal to p. Okay, and so further assume that x is a density so that you can talk about differential entropy. Then the differential entropy of this vector xn is less than equal to n by 2 log 2 pi ep. And what is this quantity? This quantity, it turns out, is the h, the differential entropy of a Gaussian random vector with mean 0 and variance p times I. Okay, that's the claim. Okay, so this is the result. As we'll soon see in the next lecture, this will be very useful for proving the capacity theorem and is of independent interest. So easy to remember, just like uniform distribution maximizes entropy, geometric distribution maximizes entropy under first moment constraint. Gaussian distribution maximizes differential entropy under second moment constraint. So how do we prove it? Okay, the proof is actually very simple, similar to the way we showed that geometric distribution maximizes entropy. So what is the proof? By the way, one property that I never covered for divergence is that divergence is non-negative. Okay, and that's just because, again, Jensen's inequality. So divergence is non-negative, and therefore, if you have this distribution px xn, I'll denote it by p, and distribution q be the Gaussian distribution. Since p has a density with respect to the Lebesgue measure, it must have density with respect to the Gaussian distribution also. Okay, I said p has a density here. I assume that, and therefore p has a density with respect to Gaussian as well, and therefore we can talk about the Redon-Nikodym derivative. In any case, it's always non-negative, and this can be written as expected value over p, as I said, over p, okay, of log of the log of 1 by the density of this guy. What is the density of q? This is the Gaussian density. So I hope all of us know this formula. e to the power minus exponential of minus 1 by 2p summation I equal to 1 to n xi square. Okay, this is the Gaussian density formula minus binary entropy of p. So this first expression here, when you simplify things, it just becomes n by 2, this first part here, log 2 pi p plus 1 by p, 1 by 2p summation I equal to 1 to n expected value under p of xi square. And by our assumption, this guy here is less than equal to this whole sum here is less than equal to p. Oh, sorry, this is log of e, which remains. So this guy here is less than equal to p. So this one here equal to p, and therefore this whole thing becomes n by 2 log. Yeah, maybe p is not a good idea here. It's np. Say it's np. So average is less than. This is just some normalization. Let's just say it's less than equal to np. That's the case in mind. But this result is true. It doesn't matter what the number is there, what number you have there. So this one is less than equal to np, and so what you get is n by 2 pi p, and then extra e here. Okay, so that's the this part, and of course this minus hp still remains here, minus hp minus hp. So this difference is greater than equal to 0, therefore hp is less than equal to this density. And remember, this is the one for Gaussian distribution. So the only thing we used here is this bound here, very similar to the proof you saw for geometric maximizing the entropy. Okay, great. So we have all our tools ready for proving the for handling the Gaussian additive Gaussian noise channel. We have defined Kullback-Leibler divergence, we have defined differential entropy, we have noticed the data crossing inequalities still hold, divergence is still non-negative, and mutual information can be expressed in terms of difference of differential entropy or difference of entropy, but you have to be careful. Only when we have densities we can talk about difference of differential entropy, and if we have PMFs we can still talk about difference of entropies. But if none of the above holds, if we neither have densities nor do we have PMF, we can't talk in these terms. Luckily for our additive Gaussian noise channel, we do have densities Wx, and therefore we can talk about this formula. And finally, we notice this property that Gaussian maximizes entropy among all random variables with a given second moment. Okay, and with this, I'll stop this lecture, and I'll see you in the next lecture.